Now for vector fields, in chapter in chapter 17 and especially in section 7.1 and 7.5, is about vector fields in two-dimensional and three-dimensional spaces. Okay. Basically, a vector field is a little different from a vector function. So a vector function is a curve that produces vectors when you have a single variable. Okay? But then now for vector field, we have within the space of any input pair or couple, you're going to associate with a vector output. Okay? So put them down. Definition. Two. What we call a function f. So we put the vector symbol on top of the notation of the function. That's assigned to each y point an alpha vector. F, so that's one. As a two-dimensional vector. So basically, the rule of this mapping is called f, and we put the arrow symbol on top to indicate that basically for whatever input pair, we're going to return a vector in 2D. And of course, you can extend it to R3. So a vector field is a function f that assigns to each couple XYZ an alpha vector compatible with XYZ. Yeah. So the output is always a vector. It's just that now we have two variables in the two-dimensional space and three variables in the three-dimensional space. Okay. That's the arguments. Okay. We express a vector field in terms of its component functions. We call PQ and R. So we have seen binary functions that are returning you a scalar. Right? We have seen multivariable functions returning you a scalar. Basically, here we're gonna use that similar strategy. So this cap, this one will return you the x and y components right in 2D. So we're gonna utilize every component as a multivariate function. It's the same for the vector field in 3D. So we're just gonna utilize PQ and R as the location. So basically, we're just saying for cap of XYZ, we explicitly write down components as P of XYZ, Q of XYZ, and R of XYZ. And to simplify the notation, we can abbreviate the couple for the arguments. So you can just write FR as a vector function equals to bi plus 2j plus rk. But this is actually a valid notation, since here we have if you're just looking at the components, it's ijk, right? So it tells you, okay, we're in 3D, and since this is a vector field, so that's indicating that, okay, we have 3 arguments and 3 components as the output. Okay. Remember that is a vector field. EQR are just scalar functions, okay, multivariate functions. Now, examples. Let's look at illustration of a vector field. True. So you can see definitely this illustration is getting more and more complicated. Now we're getting to this point of vector field. Basically, so if you think about this relationship, it's getting higher and higher dimension. So you have 3 arguments. If you are talking about 3, it's going to be 3 arguments and 3 components. The output, okay? So it's going to be a total of 6. So so basically here in R2, we're just gonna utilize the XY plane. And for every location in the XY plane, we're just gonna associate a vector to it. We're just gonna draw a. So let's say this is the input pair XY, and then we're just gonna start from this point and draw an arrow that's indicating the output vector. And possibly for different XY pair, I'm gonna associate you in another output vector. So you can see that there are infinitely pairs of XYs that you can put on the plane. So that's only an illustration, but it cannot really represent the actual vector field. Okay. So vector field could have kind of a messy relationship defined through this kind of illustration. But if you think about the vector field, it could have a more reasonable pattern. Let's say if you are looking at the magnetic field, then basically, then those vectors that are actually starting, let's say, from the South Pole and pointing towards the North Pole, right? So it's possible that for every location, it's gonna have a similar kind of pattern. It's pointing upwards. So, but basically, there are other vectors which we haven't illustrated within the sphere. Right? And basically, for whatever XY pair, then point location that you put it, you always assign a vector to it as the output of the vector field. So now instead of the dimensionality, it's getting higher. And then for more explicit definitions, or descriptions of the vector field. So now we have seen something like that before. Okay? So example. So if you think about the gradient of a bivariate function. So lambda f of xy. So this actually has two components, right? So we have f of x, the partial with respect to x, on the first component, and then the partial with respect to y on the second component. Right? So this is actually a vector field. So basically, we have the xy pair as the inputs, and then as the output, we have in the first component f of x, in the second component f of y. Okay? So this is the vector field. And of course, if you think about the gradient of a multivariable function, it's the same situation. Let's say we have a little g, and then we take the gradient. It's going to give us g sub x of x, y, z in the I component, plus g sub y in the j component, and plus g sub z in the third component. Okay. So these are definitely vector fields. So now we can adapt the notation of the vector field by putting the overhead arrow above these notations. Remark. We may also denote by number f under the vector symbol or number g under the vector symbol to emphasize that. So now these gradient operations resulted from these functions vector fields. So basically, when we were talking about the gradients for a multivariate function, it's fine. That's okay. We are not really getting into the vector fields concept. Then we don't really need the overhead arrow. But then now we are talking about vector field. Then it's highly recommended that you just keep that notation so that you just keep reminding yourself what we are looking at. Okay. Another remark. So now we have a vector field, right? So it's always returning you a vector. So you can always think about the magnitude of the output. So for the vector field, kappa equals to pi plus qj plus rk. We have it's the magnitude at any point should be a scalar function. Okay. So the magnitude of the vector field is just going to be the radical of the component squared. Right? P squared plus Q squared plus R squared. So along the line, the radical to be longer. Right. So now, since we are given the example as a vector field to be the gradient of a bivariate or a multivariate function, right? And then, so for those vector field resulted from these So these vector fields resulted from the bivariate or multivariate function. We have a special name for it. So a vector field F is called a conservative vector field. If we can find some little f such that this vector field kappa f equals to the gradient of the f. In this situation, little f is called a potential function. For the vector field that you start with. So in a way, you probably can think about this as doing an anti-derivative in a sense. Okay? But here, the only difference is that, here, for a multivariate function, let's say a little g right here. Okay? So for little g, so it's a scalar function, but if you do the gradient, you will have three components: g sub x, g sub y, g sub z. Right? So sometimes you are given the right hand side, and then they're asking, okay, what's going to be the potential function? Or essentially they're saying, okay, we have a vector field. It's possibly a result of the gradient of some multivariate function, but what's that function? Okay. So that function on the left hand side, little g, is the potential function that we are looking for when we are given the vector field. Okay. So that's why we did this kind of vector field is called a special name, which is conservative vector field. Example. So let's say kappa f of x, y, z. Let's just two dimensions. So f of x, y is negative x I minus yj. Note that so kappa f equals to lambda of little f, where so here we can simply write down little f of x, y to be negative 1/2 x squared minus 1/2 y squared. So of course, if you do the partial derivative of x, you will only get negative x. Okay, so we just have two monomial terms. And then if you're doing the partial derivative of y, we just get negative y. So exactly. So this little f is the potential function of kappa. And kappa f is conservative vector field. And then to illustrate, we can see that basically for whatever xy input, the vector that you're drawing is the negation of that vector xy. Right? So basically, you're saying, okay, for whatever, yeah. So if you give illustration, let's say xy origin. So yeah, let's just draw a bunch of integral points. And the pattern is kind of straightforward. Because for, let's say for this point, x equals 1 and y equals 2, right? For this 1, 2, then the vector that's for this vector field is -1, -2, right? So that's just from starting from 1, 2, we're just drawing the vector directly towards the origin, right? And for 2, is the same thing. So the vector assigned to the xy pair, 2, is going to be -2. That's also pointing towards the origin. And similarly for 0, 2 is going to be the same. So for whatever input pair, you're just negating the vector and pointing it towards the origin. So that's what this vector field is like. All right. So you can see that we are trying to extend the differentiation and somehow the anti-derivative in the topic of vector fields. Right? So now differentiation. So now for differentiation, let's think about the gradient operation. So let us introduce nabla as symbolically speaking. So nabla here we define this to be the following vector. Well, it's a vector operation in the sense that it will give you a vector as the output. But here we're just putting the differentiation operations right after the component. So it's going to be I associated to the partial derivative of x, this operation, plus j del y, the operation that you the partial derivative of y, plus k del z. So basically, if you remember, so if you have something like ddx, this is saying, okay, I'm just differentiating whatever follows with respect to x, right? And then for the circle thing, del x is just saying, okay, for whatever function notation that it follows, you will just do the partial derivative of x. And so basically what this whole thing is just saying is that for whatever follows, let's say little f, and then so that's the following. So for here, I'm going to do the partial derivative of x for little f, and I put it in the first component of the vector output. And then for the j component, I'm just going to put the partial derivative of y, whatever follows. So here in this situation is 0. And finally, for the k component, I'm just going to put the partial derivative of little with respect to the variable z. Okay. So this is somehow an abstract notation that we are introducing right here. Okay. This is putting a different partial differentiation operators together. Okay. So as an example, note that if you just have a multivariable function little f, then the gradient of f is exactly the thing that we have described. So which is at the I component, we are doing the partial with respect to x for this multivariate function. And we are putting the partial with respect to y of the function at component j. And finally, it's k of the partial with respect to z of that function that's following the nabla notation. Okay. So basically here we just want to emphasize now nabla originally from the partial differentiation, it was a just a notation for the gradients, but now this is a little bit more involved. This is a notation of some differentiation rule that you can summarize from above. So now we have this operation. We can start considering operations concerning this number operation, okay? And along with the vector field. Okay. So what's interesting is the following. So here, nabla is actually returning you some kind of a vector, right? And then kapf is also a vector. And it's form of a vector, okay? And then you can think about, okay, so we can dot these two things, or we cross, right? Just like vectors. So recall, when we had vectors A and B, we were doing A dot B and A cross B at the beginning of the semester, right? And now here, a nabla is a vector of operations, okay, differentiation operations. And the vector field is a vector of component functions, okay, so they are somehow different in concepts, but they have the vector form. So we are able to define certain things based on the structure. Definition. So when we dot nabla with this vector field, it's called divergence, which is exactly nabla dotting with kappa. And then when we cross, it's called the curl. So curl of the vector field is nabla crossing kappa. So they actually have physical meanings, but here, by definition, there is these. Specifically, if kappa is having P, Q, R as components, then we can write down everything more explicitly. So basically, what does it actually do? So when you think about this, so basically here, nabla is the operation that's underlined on the top of the page, right? And then if you're dotting with little f, so basically when we were doing the dot, we're just putting the x components multiplied together, right? So basically that's the partial differentiation operation multiplying by that multivariate function p, right? And then for the j component, I'm just multiplying the partial with respect to y with the component function q. And then finally for that partial differentiation with respect to z and the third component, I'm just putting that together with the component r. Okay, so we put that down together. So that equals the partial with respect to x for the p component plus partial with respect to y for the q component, and finally partial with respect to z for the component r. Okay. And then to think about the curl, it's following the same logic. Just treating that nabla operation as a vector. Okay. So nabla crossing kappa. So just remember what that actually does for a cross for cross product. So if you remember, we're just putting down everything in a 3x3 determinants. And we have ijk on the first row. And then now, nabla operation is on the second row, okay? And Cap is on the third row. So if you recall, for nabla, it's going to be del x on the first component, del y on the second component, del z on the third component, okay? And then for Cap is PQR. Okay? So symbolically speaking is this. And then we just explicitly write out what cross product gives us. So basically, to break it down into order 2 determinants, this is just going to be what. So for the leading term, it's going to be I, and then we put down, so eliminate the first row, first column. So that gives us the order 2, which is del y, del z on the first row, QR on the second row. And then without doing the further computation, let's put down j. So it's minus j, and then we eliminate the first row, second column, those rows and columns involving j, and then we will result in del x, del z in the first row, p and r in the second row, plus k. And for that, we eliminate the first row, third column. It's going to be del x, del y, q. Okay. And now we are able to explicitly write out these components. So although the first row, they are all giving you the differentiation operations, but then they are followed by a multivariate function. Right? So on the diagonal, this is del y following r. So that's just saying, okay, I'm doing the partial derivative of with respect to y for r. And then for the off diagonal, this is q and del z. So that's just saying, okay, I'm doing the partial with respect to z for this q. Okay. So this is exactly del y of r minus del z of q multiplying with I minus. So we just put the bracket, which is the result following for all the 2 determinant, which is del x of r minus del z of p, and finally plus this is del x of q minus del y of p. So this is the way to write down the calculation if you want to put everything explicitly. And we can see from the above 2 equations, for the divergence, it's always resulting in a scalar function, right? So PQR, they are scalar components, and then you are doing the partials respectively according to the definition. So this is always a scalar function, right? And for the curl, it's always giving you a vector field because now it has ijk components. Divergence of the vector field is a multivariate function. Semicolon. Oh. Of a vector field is a vector field. So now it's a vector field, so we can just put it down under another long arrow notation. Okay, so which can be written as curl of cap f, whole thing under the vector. So which looks a little bit tedious, but if you want to emphasize that this is a vector field, that's the way that you do it. Example. So let's say we have cap out of xyz. That is exactly xzi plus xyzj minus y squared. Okay. So this is definitely a vector field. So basically, for whatever xyz tuple that you look at in the three-dimensional space. So this calculation arithmetic is giving you the output vector. Right? So now let's compute the curl for this pattern. So of course, if you want to utilize the equation right on top of the page, it's okay. But here we just stick to the definition. That's going to be easier for us to. Well, at least for myself, I would say that's the method I don't really have to memorize. So we just put IJK on the top row, and then we just put down the lambda operator on the second row. So we just delta x, delta y, delta z. And then we just put the components of that in the third row. So it's going to be xz, xyz, and negative y squared. Right. Okay, so let's then calculate the components. So basically for I, we put the bracket. So here we limited the first row, first column, and then let's just compute. So what does it tell you? It tells you, okay, I need to compute the diagonal, which is the partial derivative with respect to y for negative y squared, right? So that's giving you something, which is negative 2y. And the off diagonal, we have the partial derivative with respect to z of xyz, right? So this is minus. So the partial of xyz with respect to z is just xy. Right? So you see, okay, essentially it's not really difficult. It's just a new definition, right? And then now we follow with component j. We just remember this is minus whatever result you have from the order 2 determinant. Okay. So now for j on the diagonal, this is delta x of negative y squared, and negative y squared does not involve x, so it's a 0. And then the partial derivative is right to z of xz, right? So that's x. And finally, the plus. So on the diagonal, this is xyz, we're doing the partial derivative to x, that's xyz. Minus, on the off diagonal, this is doing the partial derivative with respect to y of xz. So that's a 0. And we're done. So you can throw away those zeros, and then that will make the expression a little more simpler. So negative 2y minus xy I. So then plus x j plus yz. Okay. So this is the vector field resulted from taking the curl of the original vector field. Okay. So now, so far so good. Okay, now if it's good, then okay, we have the vector field. Now we can practice the divergence. So the divergence of this curl. So what does it give you? So remember, for the divergence, what do? So basically, for whatever vector field that we have, okay. So for the first component, that's that p. So we do the partial with respect to x for that. And then for the second component, which is q, we just do the partial with respect to y. And for the last component, we just do the partial with respect to z. And we'll just do this systematically. So delta x of the first component of the vector field, negative qy minus x xy. So just put them down. plus del del y of the second component here is x plus the partial derivative which have z of last component of the vector field. And if you calculate, so it should be a negative y from the first partial expression, and then plus 0, and then plus a y from the last. Okay, so that gives you a 0. Okay. So this is a 0, and this is actually not a coincidence. Okay, because if you think about it, the kernel is actually doing what? The kernel is actually saying, okay, I have nabla, I'm putting it in the cross product of the vector field. Okay, so this is nabla crossing f. But now divergence is doing what? Divergence is doing the nabla operation of the result that you got from the above, and doing a dot, right? So symbolically speaking, you can say this is a vector nabla dotting with vector nabla crossing vector f. Right? So, and you know nabla is perpendicular. Well, nabla is within the plane of these two vectors. So the so A dotting with A cross C. So the vector that you have for the cross is perpendicular to nabla and F, right? And then you use that original vector to dot with it. This always give you a 0. So let's put that down. Recall. Remark. The divergence of the curl of the vector field is exactly the nabla operator. So the divergence is saying, okay, I'm just using nabla dotting with whatever follows, right? And then what's following is the curl, which is nabla crossing the vector field. Right? This is always a 0. Because, well, this is doing the symbolic operation of just like A dotting with A cross B. Okay. For vectors A and B, we know A dotting with A cross B is always a 0. Okay. This because A cross B, this is a vector that's perpendicular to both M. And then if you do the dot, it's going to be a 0. Right? So this is a property that is regardless of this vector field kappa. Okay. So we do have a few properties for like that. So properties. So like I mentioned, the divergence of the curl of a vector field is nabla dotting with nabla crossing f by definition, and this equals to 0. And now, if you're doing the curl of a gradient of a scalar function. So if you think about this, this is saying what? This is saying, okay, the kernel is actually the nabla operator crossing with the vector field that follows, right? And now the vector field is what? The vector field is nabla of f. So now you can see, okay, this is this looks like a vector A crossing with a multiple of A, right? So this is eventually giving you a 0. So you can try. You can try by just doing whatever little as a symbol, and then write it down by definition. But this is essentially doing A crossing with a scalar multiplication of the vector A again. So yeah, I want to make this paragraph a little smaller. So this is always 0, right? Okay. All right. So actually now the second property here, this is very interesting. Okay. So number f is what? Number f is the gradient of a multivariate function. So here this is saying, okay, if you have the vector field that is conservative, then the curl of that vector field is always a 0 vector. So recall that f is a conservative vector field if we can find the potential function little f such that f is the gradient of little f for certain multivariate little f. So we know the following important result. If little f, excuse me, if f is a conservative vector field, then by the property right above, the curl of this vector field is always it's a 0. It's always a 0. Okay, so here basically this gives you a criteria to tell whether your vector field is conservative. Well, although it's not exactly, but basically this tells you, okay, if you start with a conservative vector field, then the curl is always giving you a 0 vector, right? So this is a property of the conservative vector field. But then later we will see that indeed, if you have a vector field and then it's differentiable at every component, then you also know that the curl of this vector field is a 0 vector. Then you can say that vector field is conservative. Okay. So this is actually a very important result. We're gonna elaborate further. Here, let's quickly do one example. So f of xyz. So let's say this is the vector field that is xci plus xyzj minus y squared k. So this is exactly the example that we have seen before. So this is not conservative. Since we have done the calculation, right? The curl here is not 0. See previous example. You know that if a vector field is conservative, that just means it will equal to the gradient of some nice potential function. Okay. And then in that case, the curl that you compute will be a 0 vector. Right? And the reverse is true if your vector field has continuously differentiable component functions. So in other words, if your vector field is nicely differentiable at every component, and at the same time the curl equals to the 0 vector, then your vector field is conservative. That means what? That means you're able to find a potential function. Okay. So Then it becomes a question how to exactly find that natural function for a conservative vector field. So this is a process that we can systematically handle. So example, so let's say we have f of x, y, z, just a vector field that is having y squared in the first component, 2xy plus e to the 3z in the second component, plus 3y e to the 3z, third component. Here, I just want to mention that the curl of this vector field, you can verify that it equals to zero vector. Okay, so make sure to do this computation for the curl of this vector field. But here, if you look at the components, they're definitely continuously differentiable. Okay? So we just have polynomial expressions, and we put together with exponential functions, right? So it's definitely continuously differentiable. So that tells you, okay, so it's a nice vector field, and the curl is the zero vector. So that tells you f is conservative. That means f equals to the gradient of some little f. So what is this function? So basically here we are looking for sort of an antiderivative in a sense. Okay, so the potential function, what do we know? We know that the partial derivatives will be the component functions of this vector field. So we have three equations. They are the conditions or pieces of information that we can somehow just trace back to the little f. Okay? So we have f sub little f sub x. So the partial derivative of little f with respect to x is gonna be the first component of our vector field. So that's y squared. And then you just write down the other two partials. Okay. So the second partial derivative is just going to be the second component of the vector field, and then the third. We just write down accordingly. Okay. So this is in a way we call a system of equations that are in terms of partial derivatives, right? Partial derivatives. So I believe in Calc 4, ordinary differential equations, you will be able to see more of these kind of questions. But here, this kind in our class is going to be a relatively simple implementations of antiderivatives. Okay, so we just do this systematically. So basically, we have three equations, and we just solve it really systematically. So that so let's look at the process. So of course, we start with one of the equations. So let's say we integrate equation 1 with respect to x. Okay. So we just need to realize, okay, so we write on the left-hand side this multivariable function. We have the notation x, y, z there. So this just tells you, okay, we're doing the antiderivative. So basically, the left-hand side is saying, okay, when we have little f, we do the partial with respect to x. Let's say we're treating y and z as constants, right? So this derivative is the partial derivative. So when you're integrating with respect to x, you are somehow saying, okay, y and z are treated as constants again. Okay? So that tells you when you integrate, you will get the constant. Okay? The constants could be functions in terms of y and z. So that's the only thing that's different from the ordinary antiderivative. So here, if we do the antiderivative, we'll get on the left-hand side f of x, y, z from equation 1, right? On the right hand side, we just write the antiderivative. Now this is y squared that we're integrating. We're integrating in terms of x. Okay. And here, okay, we treat so here we treat x as the variable and we integrating. That means y and z are constants. So y squared is a constant that you can take out. Okay, you are integrating 1, so that's actually y squared x, right? Or you can just x squared y. So the order doesn't matter that much. But then we need to plus c, right? So let's see is so I'm putting a large, basically just saying okay, it's a constant, but in terms of y and z. So what does it tell you? Instead of putting a c, I want to put a g of yz. Okay, so this constant for this antiderivative is a constant relative to x. Okay, so it could be a bivariate function in terms of y and z. Okay. And you can double check by just differentiating, okay, just doing the partial derivative in terms of x, okay? So on the right hand side, you will have y squared and then a 0, because the function g doesn't change, right? So that's the important difference from ordinary antiderivative. Okay? So this is the information, this is the fourth piece of information that we get. So basically from 1 we reduce to equation 4, where we know, okay, f has something known, and now it reduces to a function that is a bivariate. Okay, so now we just want to know, okay, what is g? So basically, as long as we know what g is explicitly, then we'll be able to track this little f, okay, based on this equation 4. So that's good. Okay, so now we use equation 1, right? So now we turn to equation 2. Okay. So by substituting 4 into equation 2. So basically, 2 tells you, okay, for little f, we do the partial derivative y, we'll get something else, right? So now let's just so now 4 is our current little f. So we just do the partial with respect to y. So it's going to be f sub y. So here by equation 4, what do we know? So xy squared, we do the partial with respect to y is going to be so x is treated as constant, y squared into 2y, so 2xy plus, okay, g of yz is a function in terms of y and z. Okay, when you do the partial, you will just get g sub y of yz. Okay, so this is equation 4. Doing the partial on both sides, right? And now equation 2 tells you, okay, this result has to equal to 2xy plus e to the 3z. Okay, this is equation 2. So putting them together, you see, okay, I have 2xy, they are the same, they can be cancelled if you just treat the second equation that you see, okay? Then it tells you, okay, now I know something more about g, right? So it tells you g sub y is e to the 3z. Okay, hence g sub y of yz equals to e to the 3z. So now we have the one more piece of information about that little function g. Okay. And then what do we know about g itself? So integrating with respect to y, we have y. So g of xy, now we're just doing the integration in terms of f, excuse me, y, right? So just do the antiderivative in terms of y. But now notice our function g in terms of y and z. Okay, so when you do the integration in terms of y, so this is treating z as a constant. Okay. Because basically here, when you do the partial derivative y, you're treating z as a constant. Okay. So now you do the integration, it will also treat z as a constant. It tells you, okay, so the integrand on the inside is gonna be a constant relative to y. Okay, so that e to the 3z is the constant, and you multiply with the antiderivative of 1, right? Plus, so once again, we need to introduce that c. But here we need to realize that, okay, we have y and z on the left-hand side. We're integrating y, let's say we're treating z as a constant. So now this c could include the part about the z variable. Okay? So now we just call it another function, h of z. Does it make sense? And you can double check, right? So on both sides, you just do the partial derivative y. So whenever you do that, okay. So when you do partial derivative y, so e to the 3z is constant, y gives you 1, and then h of z is not changing when y changes, so that's giving you a 0. Right? So that's exactly what you get for this equation. Okay. So now we know one more piece of information about g, so that can trace back to equation 4. Okay. So this is what we call equation 5. So putting through wait. So we do the substitution into 4, and we will get equation 5. Okay. So 5, 4. So putting that back to 4, that'll be the new expression for theta f, which is what we call equation 5. Okay. So we know, okay, g is now another function plus h, right? So it is x y squared plus, okay, so e to the 3z times y plus h of z. Okay, so we're just knowing more and more about the function theta f. Right? Originally, we know it's a 3-variable function, and then equation 4 tells you, okay, we know, okay, we need to look for a bivariate function in terms of y and z. And finally, we reduce to a univariate function in terms of z that we want to find. Okay? As long as we find h, then we'll be good. So finally, we utilize the third equation in the system. 5, 3 and the 5 above. So equation 3 tells you do the partial derivative of z, and you will get another partial derivative, right? So we just do that. So f sub z of x, y, z. So now you do the partial derivative of x, derivative of z for equation 5. Okay, x, y squared is a constant, that gives you 0. And now e to the 3z times y, right? Now y is treated as a constant, and then e to the 3z is her composition. So the inner is 3z, the outer is e to something. Okay, so the derivative of that is e to something times substitute the inner, and then you multiply by the derivative of the inner. Finally, for h of z, now it's a univariate function. It's going to give you h prime of z if you do the partial derivative. Right? And then we match to equation 3. So if you go a little bit above, equation 3 tells you the partial derivative of z of function f in terms of z is 3y e to the 3z. Okay? Now we match. So we know that h prime has to be a 0. Hence, and therefore we know that h must be a constant, right? So now we see that h is only in terms of z, and the rate of change is 0. So that tells you this is an absolute constant. Okay. So finally, now we know h, then we can trace back to equation 5, and we get the original function figured out. Okay. So by 5, we can conclude that f of x, y, z is x, y squared plus e to the 3z times y plus this absolute constant. That's good. So this is a really systematic process. Okay, so we want to look for a 3-variable function. Okay, we want to look for a multivariable function. Then we establish one equation out of equation 1 from above. That's equation 4 right there. Okay. So now it reduces to a problem of finding a bivariate function g, right? And then you further reduce to the identification of this little h. And finally, we know what h is. H has to be an absolute constant. That concludes this question. Okay. All right, so okay, that's pretty much all we need to know about this introductory section of chapter 7.